It's a real pleasure to see everybody, Emil and everybody in the SolidCAM family. Thank you very much for such a gracious welcome and for the partnership. We're really excited to grow the market together and really bring this new revolution of additive manufacturing, not just for prototyping, but also into mass production and this next stage of additive that I think is going to be multiples of the size that it currently is at. And so really excited to be partnering with you. And one secret of metal additive parts is all metal additive parts that are in production have some form of machining. So it goes very well together at the end of the day. Additive manufacturing lets you do really complex shapes, internal channels and other things that would be almost impossible to do with CNC. But then where you have mating surfaces, where you have interconnection between two parts, and in other key locations, you have to have tolerances that are not available with additive. So the combination of the two technologies actually is a very good fit, and is pretty much all the AM parts that are in production will have some form of either post-processing, whether it's super finishing with post-processing, or in most cases some form of very light machining, which is what makes it possible for broad adoption. And so it's a real pleasure to be here. My apologies if I seem a little bit out of it, because the jet lag is just hitting me. I landed yesterday, and then a bunch of meetings this morning, and then I'm just starting to get a little bit jet lag. But we are on a mission to eventually get to double-digit share of the additive manufacturing market, which is projected to be about $100 billion by the end of the decade. Just in concept, our company, current size, we're about 1,200 people, based in Boston. The company started out of MIT with myself and my co-founder Jonah, and then 4 MIT professors that developed this core technology to do very high-speed production with additive. We have 3 parts of our business. About a third of the business is metal sintering and technology like the shop system, like Studio, and similar products that are the most efficient and most cost-effective way to do 3D printing with metals. Very easy. It's a very good fit for a channel-driven organization that does this class of printing. We have a portion of the business that is about 90 million. It's also about a third of the business that is very focused on healthcare. You may not hear about it too much, but I'm going to show you a little bit about it. And it is the ability to print Class 2 FDA medical devices that go in your mouth and have to stay there for 10 years. For example, full arch implant dentures and things like that. We're the best in the world at that. We have a portion of the business that is printed castings, also about a third of the company. So these are very big metal parts that also need machining, and but they traditionally are made by foundry with our printers. So we have these 3 components, and as we mature our go-to-market, we want to partner and be more aligned with our channel partners so that they have the ability to really get eventually all of these products to market as efficiently as possible. And I think we have some experiments as well. Like we have a sheet metal forming process. So you take if you're familiar with sheet metal, that usually gets stamped with a die. We have a new technology that allows you to make parts fully digital. And that'll also be a product that will be very channel friendly, will be available next year. So I'll give you a little bit of a preview of that class of technology. It's a bit of an experiment for us. There's a small team inside our company developing something very novel. And so that's kind of a quick overview of some of the different things that we're doing. The areas that we're focused on primarily are 2 types of technologies. One is called binder jetting, and the second one is called photopolymer, area-wide photopolymer. Those are 2 out of 7 classes of technologies that traditionally get grouped under 3D printing. And we're primarily focused on these 2 areas because they benefit from Moore's law, meaning that They get more efficient every 2 or 3 years without us having to totally reinvent the technology. So in the case of binder jetting, inkjet benefits from the fact that you can improve the frequency and the nozzle density of heads with each subsequent generation of inkjets. And you see a chart here on the top left of how over the last couple decades, there's been an increase in the sort of laydown rate that you can do with different generations of inkjet systems. And inkjet is sort of at the heart, one of the drivers of our technology. The second one, in the area-wide photopolymerization, there's really two drivers that increase productivity over time. One is solid-state diodes. Those have a slower but a gradual increase every couple of years. But when you couple that with DMD systems that increase in resolution for a given area at a fixed resolution, over time you can polymerize more parts, and so that's also on a scalable approach. And the benefit of that latter architecture is that as those systems get very cost effective, you can multiplex them and make essentially an array, a projection array, and then have much higher productivity without a significant cost increase. And that basically means that the break-even versus conventional manufacturing for these technologies is increasing over time every decade. If you go back to the first binder jetting systems, like the MIT system in the mid-90s, that was a single nozzle system that was maybe at 200 hertz. And today, our shop system has 70,000 nozzles, and it prints at a very high frequency. So that laydown capability on a single pass basis is what's enabling the productivity improvement. To do production with 3D printing, oops, looks like we lost our, there we go. To do production with 3D printing, you need 4 things. This is different than prototyping. In prototyping, you needed something to look good with surface finish. In tooling, you need material properties and accuracy. But in production, you need 4 things. You need accuracy or tolerances. You need surface finish, whether you end up post-processing the part or directly out of the printer. You need material properties. If someone's going to buy 316L, it needs to be 316L, or it needs to be 4140, or it needs to be 6061, or whatever alloy or material. It needs to be the same thing that you would get with a different process. And then finally, you need throughput. Throughput is, at the end of the day, what gives you the cost per part when you amortize your equipment over a certain number of parts. And so that is a combination that 5 years ago wasn't there, but today we're starting to enter a zone where you could make parts very cost competitively with these processes and compete very efficiently versus other manufacturing methods. And then, as you saw from the previous curves, that throughput, as it increases, makes this process roughly, in our opinion, a 10x every decade. So you should expect that every 3 years, there's like a new generation, and then 3 turns of the crank over a decade. That's 10x, and so that's really the curve that we're trying to be on. So what do you do with these type of additive manufacturing processes? There's really 4 things that people do with metal printed additive manufacturing. One is the ability to have more sophisticated designs. A lot of people talk about complex generative design and things like that. A second one is the ability to mass customize. I think the most powerful things that you can do with additive is assembly consolidation, where you take 15, 20 parts, print it as a single component. Whether you're doing that in plastics or in sintered metal parts or with a printed casting technology, the ability to reduce the number of suppliers, simplify the complexity is one of the things that's very attractive. And then finally, print closer to the customer. And this enables you to not have to send stuff around the world and re-engineer your supply chain, and then ultimately have inventory of one for your spare parts and other things like that. So it's definitely a big driver in the business model. We've grown quite a bit as a company, and we've evolved our business model. Today we've got, since we went public We started initially with the sintered products. Today we're the #1 market share player in a dominant basis on the metal side, roughly 90% market share in metal binder jet, 9-0. There's pretty much a dominant player in it. This is the most efficient approach to do metal binder jet parts. We have a portfolio that's broader than any of our competitors, and products that go all the way from entry level up to the fastest systems in the world for mass production of consumer electronics. So we've got a pretty broad portfolio on the binder jet side. We're also the dominant #1 market share player in printed castings. So printed castings is utilizing binder jetting to make giant, very cost-effective metal parts. And if you drive a BMW, it probably has our parts in it, made with this process. If you fly in an Airbus A320, the hinge on the door, when you open the door, is made with a printed casting with our technology. So it is at scale and starting to, it continues to grow. We have a small part of our company is a company called Hydro that is the world's leader in printed hydraulics. So if some of your applications have to do with manifolds, high pressure components, anything that has fluid inside a part, we're happy to assist your customers. We are best in the world in that segment. So we're very much a leader in printed hydraulics and those class of products. I'll show you what some of those parts look like. We've got a very new technology to 3D print foam. This is on the photopolymer side. So most photopolymer systems use acrylates or acrylics in photo initiation. That's how you convert the resin to a part. We have a totally different process called photo pips, photo-induced phase separation. We acquired a company called Additive 3D that invented this technology. This allows you to use 100% two-part components in a part, so you get much better mechanical properties than you would otherwise. We use it to do foams, like a true closed-cell foam, in a number of other polymers and parts for the dental space where we have best-in-class properties. And we have the leading solution of Class 2 restorative materials for dentistry. That business is at scale, doing about 80 million and growing, and it is a growth market. My opinion is all $30 billion of the restorative dentistry space is going to migrate this next decade into printed parts. So it's a growing market. You can see the curve here. I would say a decade ago in 2010, this was a $1 billion industry for the entire revenue of the whole industry. It's about 15 billion today, so 15 times larger in 12 years. It's compounded at about 20% per year. It has had flat spots. So in 2001, it was flat. 2001, 2002, when a recession hit. 2008, 2009, it was flat for 2 years when recession hit. I'm not sure what's going to happen next year. Do we go into a major recession? But we do think it is an area of growth over a long period of time. And I see, depending on the projections, most folks believe this will get to about 100 billion by the end of the decade. So about half of the size of the machining business globally. I think machining is like 250 billion. You know better, Emil. I would say the total global parts, machines, and everything. So we'll see. So printing continues to grow. We have lots of customers globally. So the technology is being used by everything from Tesla to SpaceX to, we have parts flying in Leonardo helicopters. We have parts downhaul in Saudi Aramco oil rigs and Baker Hughes oil rigs. We have technology being used by a lot of defense capabilities and in medical devices and things like that. This is a quick sampling of customers in the last quarter. You can see lots of big brands, but more exciting, behind every one of these big brands you recognize, there's a lot of small SMEs and shops that are actually the larger volume adopters of this class of technology. So that's exciting. This is a quick snapshot of some of our polymer products. We've got a product called the Extreme 8K. It's the largest DLP product in the market with an 8K projection platform. And that's able to print materials like our new FreeFoam system, where you print the part small and then it'll expand into an actual foam and you can see the microstructure of those struts. They're actually closed cell. We're the only company that does engineered printed foams. These systems pass all of the automotive specs for UL 94, for fire retardancy, and they're quite sophisticated of a material, using that photo-induced phase separation chemistry that I was describing, that gives you a very stable thermoset with no hydrolysis. We've got a portfolio in the healthcare side. This is what these products look like, and they're able to do all sorts of dental products, and they have, thanks to that chemistry benefit, the best properties in the market. We have 3 times the fracture resistance in those products versus our nearest competitor. We have half the moisture absorption. We have almost twice the wear, the volumetric wear. So it is a great product so far. These photopolymer systems use 385 wavelength, which is a huge benefit from a point of view of not just the efficiency of the polymerization, but it allows you to do clear parts that are fully clear as well, which many of the competitive systems that are in the market aren't able to achieve. And I apologize for this screen. This is my fault, but if you saw it on the other monitors, the denture there, or that printed tooth, is really beautiful. So now back to something a little more exciting and industrial. We showed a machine that's really exciting at IMTS that will be available in Q1 to our channel partners. This is a digital sheet forming system called Figure. The sheet metal market is about $300 billion. It's bigger than machining and is bigger than additive. Right? We make cars, trains, planes out of sheet metal. That is, and today there is no good way to make a free-form shape without tooling in those markets. You always need something to stamp it, or you can make simple shapes, but with a press, but you can't make the hood of a car, the door of a car, the nose cone of a plane. You have no easy way to do that without tooling. And so we have the first of a kind tool to do that. It is a product called Figure. It can make parts as big as 1.6 meters by 1.2 meters. And I have a little video that shows you how this works. Let's see if it plays. Oops. Sorry, my apologies. Let me try to play this. So you can see the process here, forming a metal part, completely digital, with no tooling. It's okay, it's okay. It's fine. So it's very, very, very fast way to make sheet metal components of lots of crazy sizes and shapes, and for anything from defense to automotive to transportation and architecture, etc. Now to something a little more familiar, our shop system. One of the really exciting parts about area-wide printing in this class of products, like binder jetting, is that you can nest and put a lot of parts in a compact area. You can see this build box here that's packed with parts, and this is from our customer EAC in France, who's a very, very good company and early adopter of this technology. They make parts for people like Louis Vuitton and Chanel and Givenchy, etc. And you may buy a handbag and you don't know that the little metal ornament was 3D printed with binder jet. And if it's cost effective to be used in those classes of applications, it can be used industrially in lots of different opportunities and markets. So this is an exciting part. With our system, they make 70,000 of these little parts in a week if they pack a full box. So it is in a shop system, which is not our fastest machine. It is a workhorse machine for small shops. So the technology is very robust and high throughput. It's being used in surgical robotics. This is one of the most advanced surgical robots in the market. Is a vicarious surgical system, and the grippers and robotic actuation and limbs of the robot are 3D printed, which is pretty awesome. So this is an example of printing and machining. If I showed you the part is printed, you achieve 95% of the geometry with printing, and then the mating locations and where they have the fittings, there's some machining where the cables go. They put some machining to ensure that there's no abrasion on the part. It's very smooth, and our customer that designs those parts has been very successful with them in the market. And then they have staplers and grippers and all sorts of tiny components that are at the end effector, and those are also 3D printed. So this is, we have a customer of ours that makes these parts for Vicarious, and it's again a shop that would have, they use CNC for other things, but they use our technology to make those very intricate, complex parts that would have been otherwise too expensive or slow to produce out of particularly hard materials. One thing that's exciting in printing is that you can take an alloy that would have been very difficult to machine or very hard to machine, form it into a part with printing, and then just do the final touches, and so have much higher productivity to produce a high volume of parts. These systems can also print wood, so same machines like our shop system that prints metal can also print wood. So you think of wood is made of lignin and cellulose. There's two elements. When you make paper, you split that, and then you take the cellulose and convert it to pulp. This is the reverse. You spread powder, which is the cellulose, which is basically dried sawdust, and then you inkjet the lignin, and then you react it and seal it, and it forms wood. And you can print the grain and other things. So this image doesn't do it justice, but it's pretty cool to see these parts, and we'll be showcasing at Formnext a little bit more about what the shop system can do in that market. I talked a little bit earlier about what can be done in hydraulics and fluid manifolds. These are examples of real parts for customers. They would be extremely difficult to do 100% with machining because of the complex channels that you have internally in these parts. So this is a killer app for additive manufacturing, particularly for metal, and you see examples here, like there's a one-way valve that is the screw-on component here at the middle top of the page. The bottom middle of the page is also hydraulic valve, and these are examples. Our higher end systems that have inerting are able to do materials like 6061 that eventually over time will be in the more mass market products like shop. You have to add inerting and other capabilities, but this is the technology can do that, and our higher end systems can also do materials like titanium, which are a little bit more challenging. We have just to show you a couple slides of what can be done in printed castings. This is our entry-level printed casting system, which we have completely redesigned and put a single pass jetting engine on that was built from the ground up, and this is able to make parts with printed casting as long as 2 meters in size in a variety of materials. So very, very large parts. Obviously, any large part like that will have some machining as well, post-casting. These systems are like $600,000, $650,000. That's kind of the entry level. Not super crazy, but you can do incredible things with them. So here's an example of really big parts made with this. So each one of these parts is a couple meters in size with very complex geometry. So what's the difference between this and other printing modalities? Or in DMLS or laser powder bed fusion, you're roughly around $1,000 a kilogram finished part or more. In a shop system, you're 1/10 of that. In this class of technology, you are at 1/10 of a shop system for a large part in terms of cost. Now you don't have the same fidelity, and you have to cast, so it's usually not a product that's done inside a shop, it's done inside a foundry. However, the ability to mass produce at high volume, parts with high complexity that are very large, is an attractive feature, and is something that the foundry industry is modernizing. There's 40,000 foundries, very few of them have printing, and so with these new systems that are more cost effective, this is definitely a growing market. and it's an example here of a flying part for a major aerospace company. This is for a 2-ton platform. They also have a 10-ton platform. This used to be hundreds of parts. Now it's 3. And all the hydraulics and the oil lines are going through the part. So you take hundreds of parts, many of which were machined before. Now it's 3 parts with all these channels. Now this is going to get a bunch of machining afterwards for all the mating surfaces. But you're not cutting everything from scratch. You're doing just the locations where you connect with the part. So to have all the capability and the software to be able to take advantage of that is critical. And this enables a huge amount of lightweighting and efficiencies for the end customer, and is an area that's, I think, very, very interesting. I have a lot of examples of this class of technologies, stuff we're doing with Tesla. This is the hinge of the Airbus that I described. This saves them 40% weight. We have applications like what we're doing at BMW. People like Caterpillar are using this technology to scale their power generation systems. This used to be parts that would come from India, and with the pandemic, it was a huge mess for them, and so they put print capacity to make them locally. Started with 1 system that very quickly became 4 systems. Now they're looking at 12. So it looks like a model that's good for very large companies to make industrial production. If a very large company can make it cost effective, so can smaller companies. I'll just try to see if I'm going to skip a couple of these things this is one of my favorite. This is an engine from Mercury Marine. I don't know how many of you guys like boats, but I'm not a boat person, but I am amazed what these guys did. These guys had an engine in design called the Verados 600. It was during the pandemic, the early parts, and they were trying to get this engine to market. And so they used, one of the things you could do with printed castings is you could consolidate all the cores and all the parts into a single component that's got more complexity. So they did that for the engineering, and they designed this V12 engine. And when it was going to go to production, they wanted to tool it. But with conventional tooling, the tolerances are off because the stack up of like all those parts coming together. But if it was printed as a single component, they didn't have that problem. So they're in like 100% volume production this year when they launched it, and it's all with printed components inside. So, which was a cool application. Excellent. This is a V12 engine on the back of a boat. It's kind of nuts, which is nuts, with the counter-rotating propellers at the bottom. And instead of turning the engine, they just turn the silver part at the bottom, which is nuts. 600 horsepower. Oh, but that boat is, that boat is, they're 120K each. Can you believe it? You can, the engine costs just as much as more than like a regular small boat. Worth every penny. Yeah, it's incredible. Anyway, I talked to the Mercury people. They wouldn't give us a discount if we ever wanted to buy it for a boat, but they're happy with the product. So it's a cool application, and we have a few other things that we've developed that are trying to figure out how to get to market that could have great application in a channel environment. One is a new tooling technology that's a 3D thermoform process. We haven't really introduced it to the market yet. We develop it together with Collins Aerospace, but we want to bring it eventually to the broader market. And that allows you to do those big swoopy panels on the seats are made with that technology, and it allows you to pull vacuum in 3D on a very complex shape. And so hopefully that was something that we could come up with a way to expose to the whole world as we commercialize it and figure out a way to price it and get it to the market. So anyway, we're a pretty innovative company. We're very focused on bringing new technologies to market. Very grateful for the opportunity to work with all of you and move the industry forward to a new phase where people can look at new ways to produce parts and be more efficient. So I hope we're here in 5 or 10 years and we're looking at a much bigger industry and made a lot of customers successful. So thank you for the opportunity. Thank you.
I have a question. What are the next planned materials for the shop system?
That's a great question. I don't want to confirm it, but I would love to do copper. I got to find a way to do copper. And we have a multi-generational roadmap for all of these systems. And we have Inconel 625 and 718. I think we've announced 625. We haven't announced 718 yet. We will continually add capabilities and materials to all of these systems.
What about titanium?
So titanium requires inert gas. Titanium can be done on a eventually, one day there will be a shop 2 and that will have inerting and it'll do titanium. But the shop 1 doesn't have inerting. So maybe give us 2 years or a year and a half. So. So we have some, depends on the type of part and components, but we have systems that are in the air with different techniques. Yeah, so the way that the parts that are flying have been basically certified by the companies directly, not with us creating a procedure, but like Leonardo and Hydro have a component flying in helicopters. On the printed casting side, we have that hinge, for example, and there's many that's in a plane. There's a component on the Trent engine from Rolls-Royce that is something that they've done also on the printed casting side, but that's them doing all the work and getting it in the market. So I think over time we will mature this and then develop all the standardization of procedures to basically get this at scale into flight critical. The microstructure of the metals is of great interest in the repeatability of the process and all of that. And when you do processes like laser powder bed fusion, which have a lot of investment going into it, they still are having issues with things like fatigue and other issues. And I think that one benefit of either printed casting or sintering is that you get microstructures that are well understood, and so we hope that it'll go faster than it's gone on the laser side. But yeah, you can, if you were, obviously the shop system is a very, I wouldn't call it a very narrow product, but it's a product that fits a particular category. But if you were doing flight critical hardware, you would probably want to use a furnace that allows you to tune the cooling rate so that you get, let's say if you're doing 4140, you can tune it to get bainite, pearlite ferrite, or martensitic, etc. So you have a little bit more sophistication. But if you're doing flight critical hardware, you're doing more advanced stuff, like a structural part or something like that. Yeah.
A real quick question: do you see SolidCAM having the same importance? Like obviously in a printed cast, there's all these tolerances and things like that. But it seems like sheet metal, you guys are well ahead of the curve. Does SolidCAM have a place in that market?
It could. I mean, we have to sit down and talk about it, but we have no idea how we're going to do the trimming right now. We can do the forming, and then people have to figure out the trimming. They got to scan it and trim it, but there's a lot of laser and hemming and automated tools to do this stuff. That's all CAM related. Somebody would have to develop the software for it. I mean, SolidCAM's a fantastic product.
I'm aware.
Yes.
Thank you.
Absolutely.
What do you think of the hybrid CNC machines where they're adding a laser head on a CNC machine? There's a future for that?
Well, I think they definitely are. There's many techniques to do hybrid CNC machining. So where do I start on this? When you have you have a productivity issue, there's a few issues. First, it's a good technology for a reasonable group of parts. You have when you deposit metal, then you have to wait until it cools down before you can start really machining. So productivity is an issue, and then the type of depending on what process you're doing to deposit that metal, there are many approaches, whether it's like a welding type approach, blown powder approach. There's some very high speed, high speed as in like the speed of the powder hitting the part techniques. there's a series of ways to add volume to an existing part, kind of like in a repair mode, and then subtract it. Productivity of that process is really usually the bigger question. Ability to do some geometries that are quite complex, but it's one of the approaches that is continues to be used and increased in popularity. Particularly for large parts, it makes sense. I'm familiar with with several large companies that are exploring it.
We noticed that many machine manufacturers are starting to have this special type of machines adding additive to their CNC machines, so they must see a market for it.
Yeah, they're well. If this is the type of machine you make, it probably adding a head to add metal is probably one of the more practical ways for them to have a play in the market. It's a thing. Yeah, I would say. We're going to see a lot of innovation over the next. One benefit of area-wide processing is you can do lots of components at very high throughput, but there's still a place for a vector-based process where you're adding and subtractively removing. So it's going to be lots of ways to make metal components.
I mean, 3D printing is like magic. You give the model and it comes out.
Yeah, you always have some type of post-process which is good. Awesome. Thank you very much, everyone. Thank you, Emil.